And we'll get going. So welcome Tuesday, November 3rd, class session. And our mission today is mostly going to center on graphing. Graphing rational functions. Let's finish up the chapter we're currently in. And then we're going to talk about a new class of functions. So we organize things based on what kinds of functions they are. So we talked a lot about rational functions and what you could do with them. So the next thing we're going to talk about is, in the next chapter, radical functions. Functions that involve radicals, or in common English, roots, square roots, cube roots, things like that. And we'll begin by graphing some basic radical functions. So that's the plan for today. And any questions you'd like to ask. So where should we start? I think I'm going to start just orienting us. Let's look at the website because I've added some new handouts that might help you. And you just want to take a look at those. So I'm going to share our website. Got it. Okay, now we're looking at the web page. Got it. Let's make sure we're in the right class. Math 119, week 10. Excellent. So this is what I was saying. We're going to finish up chapter 6 by graphing some rational functions. And they're actually kind of fun to graph, not too fancy. We're going to not do fancy ones. You can always make things fancier. And then we're going to talk about roots, radical functions. And we're going to talk about that for several sections here in chapter 7. Different things we can do them, just like rational functions. What did we do with rational functions? We simplified them, then we added them, subtracted them, multiplied them, divided them. We're going to follow the same program for radical functions. Simplify, add, subtract, multiply, divide, and then eventually graph. Now here in this chapter, he puts the graphing towards the front. So that's what we'll start with today. So today is kind of a graphing theme. You're keeping your eye on your homework, and you know that you have a homework due tomorrow, homework number 7, and you have some XYZ homework due tomorrow. And later today, I think I'll turn on homework number 8. Just haven't had a chance to turn it on yet. Then you can get into that for the next week. These are some of the handouts that we have. Okay, good. I'll make a note of that. Thank you, Jacob. We can start with some questions like that. These are some handouts that we've been giving you, but I added a new batch down here. Radial functions. Okay, I've got a typo. It's radical functions, not radial functions. I think I better go behind the scenes and fix that right now, because not only that, there's no bullet there. So something must be really bad in my HTML. Let's just fix that right now. I see it. I left out a tag besides misspelling things. Okay, fix that. Upload correction. Reload page. Okay, now we feel better. Radical functions. So here are some handouts about radical functions that are going to be really useful over the next 2 weeks. We're going to be working on this week and next week. And not all of these we're going to use this week. So I think maybe the first 3 we're using this week and the last 2 we'll get into next week. But just telling you more things about doing radical functions, simplifying them, graphing them. The graphing one in particular is very detailed. Let me pop over there, show it to you. So I wrote this, I can't lie to you, I wrote it in 2008. So, you know, over time, let's get someone else in the room, excuse me. Over time, I just collect things, you know, like you just collect things and collect things and collect things, and then all of a sudden you can't put your car in your garage because you've collected too many things. Well, I just wanted to write this up really nicely in 2008, how to graph radical functions, and people have liked it, so I've kept it. So here I'm giving you a super detailed explanation about how to draw radical functions and you know what the shape of the square root is and how can you scale it or translate it. Just that means move it up, down, left, right, shrink, stretch. Shrink, stretch. Did I say that incorrectly? And that's a square root, and of course then you can do it for cube root. And you can do the same with a cube root. Move it up, down, left, right, shrink. I said shrink. Shrink and stretch. I can't speak straight. Now you cannot read these while I'm scrolling through them like this. And you won't read them in 5 minutes anyway. But if you want to look at this carefully, this handout really gets you going on graphing radical functions. Hopefully make it as easy as it could be made. So take a look at this handout, Graphing Radical Functions, posted on the website. And the other ones as well. I also want you to remember this really old handout because we've been doing, you know, maybe more algebra than graphing. And maybe a long time ago, I showed you this handout and said, you know, here are some basic graphs. Here are the key points of some basic graphs. But we haven't been doing lots and lots of graphing. Now we're going to do a little more graphing in the next time period. Because the more complicated the function, the more valuable the graph is to us. It tells us what things look like. So you've drawn lines. We've even once drew absolute value. We haven't drawn a lot of those. Drawn a parabola. Maybe we're going to draw parabolas in great detail later. Square root function, that's on the ticket today. Cube root function. Reciprocal function. That's something we'll talk about today too, because it's like a rational function. This is the graph of a rational function. And then some others we might talk about later, exponential, logarithmic, stuff like that. So I don't want you to forget this handout, which kind of showed you like the basic shapes in the universe, or the basic shapes in the math universe, or if you like, the basic shapes in the Math 119 universe, in the intermediate algebra universe. So don't forget that you've seen this handout, or at least you've had access to this handout. Basic graphs, key points of the basic graphs. Okay, good deal. So we're going on there, and we'll post videos, of course, and we might use a little Desmos today too. Okay, so let's go back to our paper, and Jacob gave us some good questions here. Let's take a look at those, and then we'll jump into our topic. Let me just pull this up. 6 examples or exercises 4 and 17. Four and 17. Tour bus, blah, blah, blah. Driver drives faster than usual. That's not a great idea. Oh, we know what that is. And number four is a really basic problem just in interpreting words. So why don't we scratch out both of these really quick? And why don't we scratch them out on the board? So if you're watching this video later, I mean, you can consume this in the video. I'm just going to carry this over here. And it's mostly so I can just stand up and not sit all day. But then I'm not in front of my screen. So if you want to get my attention, just yell at me while I'm standing up here. So sum of a number and twice its reciprocal is 27/5. Find the number. That's short enough to write down. The sum of a number and twice its reciprocal is 27/5. Okay, this is going to be a problem that involves rational equations, but it's also going to be a great example to graph in a second. So I like this problem. Thank you for asking it. And let's just run through it really quickly. So what are we looking for? We're looking for a number. We're looking for the number. So that means we're looking for one number. What is the one number we're looking for? A number such that when you take the sum of that number and twice its reciprocal, you get 27/5. There's some equation here. This plus this equals this. So start by saying, let x and y, whatever, let x be this number. We just name it. We don't know what it is. That's the variable. So now sum. Sum means plus. Sum of two things. A number. That's the number we're talking about. Twice its reciprocal. Reciprocal means to flip it over in common English. Reciprocal of 5 is 1/5. Reciprocal of 2 is 1/2. Reciprocal of -3 is -1/3. You just exchange the numerator and denominator. But if you don't know what this is, not even if it's a fraction, reciprocal is 1/5. I'm sorry, 1/x. But it's not x plus reciprocal, is it? It's x and twice the reciprocal is 27/5. So that's like 90% of the battle is to write the equation. I guess I could simplify it by saying 2/1 times 1/x is 2/x. Okay, so here's something to solve. And then later today is something to graph too. So it'd be very interesting to graph this. So let's keep this in mind. Now remember, when I solve, I think the first thing I want to do is make sure I don't divide by 0. So right away, I see that I cannot use 0 for my answer. I just make a note of that so I don't forget. But how do I do this problem otherwise? Let's get rid of the fractions. Let's multiply both sides by least common denominator, 5x. I'm not doing this with lots of writing or lots of explanation. I'm just doing this straight ahead. So what we got right now is 5x squared. I multiply this one, multiply here, 10, but the x's cancel, plus 10. Here I multiply, the 5's cancel. I get 27x. Here's something that I might factor and solve by factoring. But I have to get everything on one side. So 5x squared minus 27x. 10 equals 0. And then, not stand in front of the camera, the minus 27 because I subtracted 27x. Then we just take a shot at factoring it. First, we'll just guess and check. 5x is squared is x times 5x. That's a possibility. Now, how can I do 10 so I get 27 negative in the middle? 5 times 5 is 25. 5 times 2 is 10. Here's a 25 and a 2. 25x, 2x. That could be 27x, but I need to make it minus, and I need to make both signs the same. So we just double check that that works. 5x squared, yes. Minus 25 minus 2 minus 27x, yes. Plus 10, yes. Okay, so now I've solved the problem. Either x minus 5 is 0, or 5x minus 2 is 0. That means either x is 5, or add 2, divide by 5, x is 2/5. How do I feel about those answers? Well, they're not 0. And I was forbidden from using 0, so I'm okay with that. Do they work? It can't be too bad to see if they work. Let's try it out. The number plus twice its reciprocal, is that 27 over 5? Well, this is 2 over 5. 5 converted to fifths is 25 over 5. And so, yes, that one works. Let's try this one. A lot of different color. So that number, whoops, I pulled out a different color, but it's out of ink. That number plus twice its reciprocal. Okay, I'm going to have to think about that for a second, but twice times 5/2, that's nice. That's a 5. This is 2/5. And of course that is 27 over 5, because I just did 5 plus 2/5. So that's interesting. There are 2 ways to do this. What is the number? Well, it turns out there were 2. So these are the 2 numbers. Okay, so that's a really good problem. And I only want to do this now. How does that solving relate to graphing? So that's what we're going to show you today. So I'm going to write this down in the corner so I can use it later. What would happen if I tried to graph x plus 2 over x. Now I'm curious. Think of that as a function. And what am I going to do with this 5 and this 2/5 and this 27/5? So I leave that in the corner so you can come back to it. Now, since it's erasing, now I'm going to erase. Of course, after I erase, you can't keep copying it down, but then you got this recorded on video. Oh, you know what I forgot to do then. See, so you can do things on your screen, but that's why I got to practice this. And I don't know if I did that earlier. I have to like train the camera full time on that screen. So I may have forgotten to do that. I apologize. You can still watch the video, but it'd be more useful if I trained the camera on the board for the recording. Okay, you said number 17. So is that something I'd like to graph? And that's why this is relevant to today. Tour bus leaves Sacramento every Friday at 5 p.m. for a 270-mile long trip to Las Vegas. This week, the bus driver leaves at 5:30 p.m. to arrive in Las Vegas on time. The bus driver drives 6 miles per hour faster than usual. What's the bus's usual speed? It's 270 miles. So this is, definitely a rate times time equals distance problem. And I'm not going to write down all the words because there are too many words. And you have the words printed in your book. So let's just assemble the chart we did. Rate times time equals distance. And let's fill things in while we read the problem. There's a very rough sketch here. I'm not trying to do this super neat. So, tour bus going to and from Las Vegas. Actually, in some sense, they're only talking about going to Las Vegas. And I guess the difference is usually it leaves at 5. Now it leaves at 5:30. So I don't know what to call these. Why don't we call this normal and late? I do know what the distances are, though. Driving from Sacramento to Las Vegas, they say 270 miles. I assume the author has got the mileage correct. I've been in Sacramento, I've been in Las Vegas, I've never driven from Sacramento to Las Vegas. What do we not know? We don't know how fast the driver is normally going. But we do know that since the driver started late, he went a little bit faster this time. So I don't know what the normal rate is, but I do know that on this trip when he started late, he said he was going 6 miles per hour faster. Let's see if we got that right. 6 miles per hour faster than usual. Now, what is the bus's usual speed? Now, this is interesting. What about the times? I can't say they take the same time, right? Because this day they started late. He's trying to get there faster. He's trying to get there in a shorter time because he started a half hour late. But I think that's the key, that these times are different by a half hour. Normally it takes them 2 hours. This time it takes them 1.5 hours. I don't think that's right though. But I can compare these times, not that they're equal, but one is 30 minutes less than the other. I also got to think about 30 minutes. I got to think, normally you measure speed in miles per hour. So I got to think that these differ by 1/2 hour. So what differs? Remember how you can fill in the middle? In the problem we did, 270 over x, 270 over x plus 6. And now here's the key trick. Are these two times equal? You say no. He started late. This time is shorter. He's going to drive less time, but therefore he's driving faster. How much shorter? 30 minutes shorter he's going to drive. 1/2 hour. So I'm going to add 1/2 hour to one of these sides. And we got to get it straight which side we're adding 1/2 to. These are not equal, but if I add 1/2 to the right side, the correct side, excuse me, they will be equal. On this problem, the correct side is the right side. Why is that? Because this number is smaller. He started late. He's going to drive for a lesser time. He's going to drive for a smaller time. 1/2 hour smaller. When I add a 1/2 hour to this, it will match the normal time. Okay, now I feel good about the problem. And we're going to try to do it just like we did the last one. Multiply by the least common denominator. This might make a good graph too. And the least common denominator is 2x, x plus 6. So we're going to say, I can't do anything except multiply the three denominators, really. This person is missing an x plus 6 and a 2. So that's what I have to supply. This person is missing an x and a 2. Denominator. That's what I have to supply. This person is missing an x and an x plus 6. So that's what I have to supply. That's the least common denominator. Now when I multiply it through, I cancel an x on this side. So I have 2 times x plus 6 times 270. I think I got to multiply that out, but let me just write it. This time I multiply first and I cancel an x plus 6. So I have 270 times 2x. Then I multiply here and I cancel the 2 and I have x times x plus 6. Okay, so these numbers are a little bit larger than I might wish for, but I just have to deal with it. So let's multiply everything out. 540 x plus 6. That is 540x. Yuck. 6 times 540 is 3,240. Over here, it's 540 x's. And here is x squared plus 6 x's. So I got one, slightly positive thing that's going to happen. At least I get to cancel out 540x.
Hey, Professor, I have a question.
Go ahead.
So I'm wondering, wouldn't it just be 1/2 x squared because the 2 would have canceled out, wouldn't it?
Good. Let's think about this. Let's double check. The 2 did cancel there. So I can't, no, after I multiply that times that just turns into a 1. There's no half left.
Ah, I see. Okay, thank you.
Is that what you're asking?
Yeah, I got it. Thank you.
Yeah, literally, you only multiply by 1/2 once, just right there. Yeah, you're not distributing the 1/2. For example, if you said 1/2 times x times y, you don't say 1/2 times x times 1/2 times y. You only use the 1/2 once. Okay, good question. So let's get these things together. Like, let's bring the 3240 over to the other side. Thankfully, I canceled the 540x. But I'm going to have to factor this monster. Subtract 3240 from both sides. Now, ordinarily, I'm not thinking always about a calculator, but this time I might even say give up and let's work it out on a calculator. I mean, I need 2 numbers that multiply to 3240 but differ by 6. Now, you guys work that out if you want. I could do 81 times what? 40? Would that be 3,240? Yes, but it doesn't differ by 6, so that's not going to work. So let's shove some numbers this way. Let's say, wow. Now, 81 is 9 times 9. 40 is 4 times 10. If you know the numbers, if you see them, shout them out. But I'm just going to say, can I work it out without going straight to the calculator? What if I took a 3 over there, made it 30? No, I need something bigger. Take a 3 over there, I need 60. Take a 3 over there, take a 2 over there, 6 times 54. Okay, I'm just fiddling with the numbers, but 60 times 54 is 3240. Is that right? Yes. Because 6 times 540 was 3240. Good, and they differ by 6. I think we hit the jackpot. X times x is x squared. 60, 54. Let's get the signs right. I want to be plus 6. I want this to be positive, this to be negative. Okay, that wasn't so bad. I thought that number was too big to deal with, but we just had to play with it for a second. Okay, x minus 54 is 0, or x plus 60 is 0. X is equal to 54, or x is minus 60. Okay, now let's think about this. I did not, at the beginning, I broke my own rule, right? I said at the very beginning, I should always make a note of what was forbidden. So what's forbidden is x equals 0 and x equals minus 6. I cannot use those. Thankfully, my answers were not 0 or minus 6, but I think you see that one of those numbers is bad. Even though it's a good math answer, it's a bad answer for this problem. Which is the answer I have to throw out over there? You can type it in the chat window too, but I'm not looking at my chat window. Which one of these answers do I have to reject?
The negative 60.
Because it doesn't make sense in the problem. That's right. I cannot drive the bus negative 60 miles per hour. So it's got to be 54. Let's just test it. 54 miles per hour, 60 miles per hour. Now I'm going to have to do x plus 6 is 60 if x is 54. So what's 270 divided by 60? That's 27 over 6. Divide by 3, 9 over 2. That's 4.5 hours. What's 270 divided by 54? I'm just doing scratch work right now, so I'm making a mess on the board. This 27 over 54 is 1/2. And then times 10, what am I saying? That doesn't sound right.
It's 5 hours.
Oh, it's exactly 5, isn't it? Yes, it's 1/2 times 10, which is 5 hours. See, that makes sense. I was expecting the numbers to be the same. And then I remembered, no, he was starting later. He's driving faster. So they do differ by a 1/2 hour. Perfect. Okay, very, very good. Now, what do I want to say here? I bet this would be worth graphing. Again, I bet this would be worth graphing. So I might erase all of this, but I'll leave it on the whiteboard so we can go back to the paper and graph. What happens if we graph? Look at the things in black. 270 over x and graph 270 over x plus 6 plus 1/2. And what does that have to do with 54 and minus 60? So I'm going to give you a reason for graphing. I want to show you that graphing is another way of looking at the problem. Okay, what else do I want to say about this problem? Like I said, I've never driven from Sacramento to Las Vegas, but 4.5 hours, 5 hours sounds decent. I lived in Southern California, so I have been to Sacramento, but not very often. Sacramento's kind of northern California. He was driving faster, so I was worried, but he's not driving too bad. 60 miles an hour average. You're going to cross some mountains, maybe. So yes, he's not going to be averaging 80 miles an hour. Okay, everything looks reasonable in this problem. So I like it. I like it. So now let's talk about graphing. We have two excellent things we could graph. Let me get rid of this pen that I threw out. Okay, perfect. So it's just a basic idea saying, if you ever have a question, we can definitely work it into anything we're doing on that day. So let's graph these things. 270 seems like a large number, but we can deal with it. Those are not going to be the first things I graph. Well, very close to almost the first things I graph, but I'm just putting this on the board. We are suddenly very motivated to graph these. So let's graph a basic rational function. You really do want graph paper. Graph paper make your life easier. And here's the most basic rational function in the universe. Like 2 over x is relatively simple. That's why I said, no, that's a good one. But how about just graphing 1 over x? What if I made a picture of 1 over x? That picture depends heavily on the scale I choose. So I'm thinking about what kind of scale should I choose. Let's be generous. Usually it's not a smart idea to pick the scale before you make the drawing. But this is a preliminary drawing. If we don't like it, we'll tear it up and draw it again. This is not like chemistry class, where if you're mixing stuff together and it doesn't work, well, then you got to start from the beginning because you just got, wasted all that material, right? Here, maybe I'm using some paper, but not much else. So let's make a chart of x and 1 over x. A little bit sloppy right there. Now, from the very beginning, I admitted that I cannot put every number I please into here. I cannot put in x equals 0. There is no such thing as 1 over 0. So just like solving equations, I think I'll write that down. Don't do this. That's a terrible looking 1 over x. Sorry. I just looked at my screen and saw how bad that looked. 1 over x. Cannot put in 0. Don't do that. But there's some numbers I can easily put in, like 1. If I put in 1, I get 1 over 1, which is 1. If I put in 2, I get 1 over 2, which is 1/2. If I put in 3, I get 1 over 3, which is 1/3. If I put in the opposite of those numbers, I get the same results, just with minus signs in front. Minus 1/3, minus 1/2, minus 1. I could even put in more points. Maybe I will, but let's start like this. So 1 and 1. 2 and half. 3 and a third. A third is hard to mark. So you just do the best you can. Let's say that that's about a third of the way up. Oh, and the same points on the other side. Minus 1, minus 1. Minus 2, minus half. Minus 3, minus 1/3. Now my letters got in the way. But I can take other reciprocals too, like the first problem you just asked. What's the reciprocal of 1/2? The reciprocal of 1/2 is 2. So I've got some other points I want to try. What happens if I tried 1/2? Reciprocal of 1/2 is 2. What happens if I try 1/4? The reciprocal of 1/4 is 4. Let me mark those quickly. 1/2, give me a 2. 1/4, give me a 4, which is off scale because I planned my scale badly. 4, give me a 1/4 right here. I can also put in -1/2 and get -2, -1/4, and get -4. So that'll give me these points. At -1/2, -2, -1/4 is 1/2 of 1/2 down here at -4. -4, give me a 1/4, which is 1/2 of 1/2. Put a dot right there. Okay, so my scale isn't beautiful, but I can adjust. But I'm interested in the trail of these red dots. You know, if I put in a 1/3, I'll get 3. Hard to mark 1/3, but I'll do my best. Put in a -1/3, and I get -3. It's about right there. And now you see on this image, and drawing things by hand is also very slow, sure, but you see a clear pattern. And if I connect these dots, just gently connect these dots, you see the same pattern that I showed you on that handout. This image was on that handout. This is the graph of 1/x. The bigger the number I put in, the smaller the answer becomes. Like if I put in 10, I get 1/10, right? And the smaller the number I put in, the bigger this becomes. If you take 1 divided by a small number, you get a big number. And I can put in any number I please except for 0. 0 is right here. It's the y-axis. And that means I cannot touch this. I set it in my table, but I want to draw it on my picture. Can't touch this, you know. Do. Maybe that was too long ago. You cannot put a dot at x equals 0. There's a natural break in this graph. Now, after you look at it for a while, and after you accept the graph, you say, okay, there's nothing remarkable about that. Why should you make a big deal about that graph? Well, I make a big deal about this graph because it's like your first rational function. And every other rational function you draw in some way is going to look like this. Excuse me. I wanted you to show this picture right here, right? I want you to keep this picture in your mind. But I also want you to look back up to here that we wanted to draw this, right? So what happens if I draw 2/x? Well, like the problem said, isn't it just twice 1/x? That's how you could think of 2/x, 2 times 1/x, right? So what would this graph look like? I think it would look like the graph we just drew, except let's reason how it would be different. How would it be different? Instead of 1/x, if I had written 2/x here, you know what I would be doing is I'd be doubling each of these people. Instead of insert a 1 and get a 1, now I insert a 1 and I get 2 times 1. I will be doubling each of these values. Let's write it out. X, 1 over x, 2 over x. Still, I cannot put in 0. Doesn't matter whether the 2's there or not. But if I put in 1, for 1 over x, I get 1. For 2 over x, I get 2. If I put in minus 1, for 1 over x, I get minus 1. And for 2 over x, I get minus 2. And I claim that that's going to be the pattern all the way through. All I'm going to do for my y values is double each y value I used to have. Now, in order to draw that nicely, I think I might have to shrink my scale. And even that might be not good enough. So we'll just do the best we can do. You also know this, that, if I didn't want to work as hard on this drawing, but it's good to work on this drawing, I could have the calculator or computer Desmos draw this. I think we will. But I just want to give you a good idea of what you expect it to be first. If you know what it's like before you start, if you know what it looks like, then you can tell whether or not you made a mistake. Okay, 0 cannot go there. Just draw a dotted line there, a dashed line. That's like a wall that you can't touch. The fancy word is asymptote. Asymptote means the graph gets closer and closer to that line, but never touches it. Well, yeah, I should be careful. Theoretically, it could touch it, but so right now it doesn't touch it. Okay, so now it's put in 1, and I got a 2. Put in 2. Ordinarily here you'd get 1/2. Now you'll get 1. 2 and 1. Now if you put in 3, instead of 1/3, you get 2/3. And if you put in 4, instead of 1/4, you get 2/4. 2/4 is 1/2. Do you see it's behaving the same way? Let's try plugging in a half. If you plugged in a half, you used to get 2. Now you'll get twice that, or 4. And if I plugged in a quarter, I used to get 4. Now I'll get 8. Okay, so this looks very much like the last graph, except it skyrockets faster as you go towards the origin, and it levels off slower. Now, I've only drawn half of it, right? Because I know that if I had used negative signs in front of any of these numbers on the left, I would have got the exact same values, but with negative signs in front of them, like -1, -2, -2, -1. I just have to reverse the y values. I just have to multiply by -1. That's kind of a nice problem in that sense. 1/2 I get 4 negative. 1/4 I get 8 negative. And I'll get the exact same points, the mirror image of them below the x-axis. Now I've graphed 1 over x on the left, 2 over x on the right. But I cannot get them both on the same paper at the same time. your first reaction is, oh, they look the same to me. And they were drawn at different scales, so it's hard to compare them too, right? Okay, this is where Desmos comes in. Let's draw them on the same picture. So I'm going to pop over to Desmos, just so I can type them on the same screen. Okay, let me get that situated nicely. I'm not going to log in right now. I'm just going to use it. Y equals 1 over x. Y equals 2 over x. I mean, literally, do you see that? Let me zoom in a little bit. The 1 over x is red. The 2 over x is blue. And all I did was doubled the height of every red point. There's a point. It's not going to let me highlight that, right? Okay, I'll do it myself. There's 0.11. And what does it look like on the blue graph? I just doubled the height, and now it's 1, 2. Not 2, 1. 1, 2 is doubling the height. The height is the second coordinate. What's the height right here? Looks like about 2 and 0.5. That means 1/2. And what happens if I double that height? I should have height 1. Yes, I do. So graphing 2 over x was not hard if I knew how to graph 1 over x. Okay, now I want to shock you, but I want to shock you faster. So let me make this picture larger. And it's kind of productive to mess around with Desmos like this. Let me turn this off. You don't have to erase things if you don't want to. You just click on that circle and turn them off. So now let's take the function 1 over x, which here is in red, and now let's compare it to the function 1 over x minus 4. Oh, watch this, like instant gratification. There's 1 over x minus 4 in black. How has it changed? If you look at this, the asymptote, the no-go line, was the y-axis. But now it looks like I'm approaching x equals 4 as my no-go line. Does that make sense? Yes, I cannot use 4. You see that right there. Like if you plug in 4, you're dividing by 0. That's illegal. So what happens when I change the x to x minus 4? I just shifted the graph left or right. In fact, if you want something really cool, just change that to a k. Desmos says, would you like to have a slider with that? I'll say, sure I do. And every time I change the k, I do what? I just move the graph left or right. See, if I says k is 5, then I have moved it 5 units to the right. Now be really careful about that. X minus 5 means the center is at 5. So I moved it 5 units to the right. But x equals minus, or k equals minus 5, that would be, let's try it out. 1 over x plus 5. Okay, confirmed. Notice that 1 over x plus 5 moves the graph 5 units to the left. Now it's centered at minus 5. That's where the disaster is, minus 5. So what I just did right there is fancy words called horizontal translation. I translate the graph horizontally. Now, let's get up for the next surprise. Oh, by the way, I want to point out that in all the graphs that I just put up, do you see that y is never 0? Let's turn this off, and let's turn this off for a second. Look at the red graph closely. I can never put in x equals 0. That's forbidden in this red graph. But do you notice that also y is never equal to 0? Do I ever cross the x-axis? That's when y is 0. And the answer is no. 1 over x is never 0. I'll go back to my paper for just a second. Notice that 1 over x is never 0. 2 over x is never 0. And why does that work? Somebody asked me this question this week. I thought it was a good question. Do you remember that if you multiply 2 people and get 0, that means that one of those 2 people is 0? Oh, see, now I ran past my break. Okay, let me write this down, then we'll take a break. If you multiply 2 people and get 0, one of those people got to be 0. But if you divide 2 people and get 0, you cannot say that one of these people is 0, because you're not allowed to use this person b equals 0. You're not allowed to put 0 down here. So the only way for a fraction to be equal to 0, this is really important, is if the numerator is 0. So could the fraction 2 over x ever equal 0? Could the fraction 1 over x ever equal 0? The answer is no, it's impossible. And that's why you never see a black dot on this line, y equals 0. Think about the x-axis as the place with no height, the place where y is 0. Okay, that's really important. Okay, so having so much fun, we ran right past the break. So let's say coming back at 113. So am I counting right? Yes. Okay, and we're going to do some more graph of this, and then we'll get to graphing things that you asked me about in those first 2 problems. Okay, I'm going to mute my microphone just while I get up and stretch my legs. And we'll come back in 5 minutes. Easy, easy. Okay, we're still on break, don't worry. But Rabbit wanted to say hi. So I think you guys are working too hard. So Rabbit's gonna say, don't work so hard. Okay. Oh, this is like, I can appreciate that this gets boring sometimes. So Rabbit just wanted to say hi. No, Rabbit doesn't like the tabletop because it's not soft enough. Okay. I'm going to let Rabbit go. Oof. Okay, go find your home, Rabbit. Okay. Just had to get some levity in there. I picked up a cold over the weekend, so felt kind of mushy and miserable. Okay, let's go back to the paper. Let's go back to work. And the Rabbit is exploring the basement. It's kind of like a cat. Rabbits can be litter trained too. Okay. Let's go back to Desmos because, I like graphing things. I like graphing things by hand. But the Desmos kind of accelerated our graphing a little bit. So I moved the graph left and right by subtracting a number from the x. Could I move the graph up and down? That's actually a little bit easier. What if I had put the k on the outside? Take out this k down here. And what if I had said, let's look at 1 over x and 1 over x plus k on the outside, kind of adding k to the y value. The y value is 1 over x. If I add k to that, like here, I subtracted 3. What happened? The graph went down 3. If I add 3, if I say plus 3, the graph goes up 3. Okay, that's kind of practical. So now I can move the graph left, down, and upright. Could we do both at the same time? Let's switch K. I need another letter. So how about H? How about subtract H, add K? Now notice how Desmos says, do you want another slider? So sure, I like the first slider. Let's have another one. So now this black graph can be moved left and right and up and down. Rabbit feels trapped, so he's coming back upstairs. But I want to show you something about this graph. So on the piece of paper, I may have hang on, rabbit problem here. Okay, small rabbit problem there. So what happens when I subtract 2 from the x, but add 3 on the outside? I have this feeling that I moved the graph two units to the right and 3 units up. How can I draw that quickly? Well, remember, in my original graph of 1 over x, this is my original graph. Remember, I never touched this line, the x-axis. I never touched this line, the y-axis. So think of the x and y-axis as a skeleton that this graph is hanging on, like your skeleton, kind of defining how tall you are, how long your arms are. So what if I moved this frame, the x and y axis, 2 units to the right and 3 units up? Then the skeleton would be here and here. Let's say that that's a 3 and that's a 2. But otherwise, the shape of the graph should stay the same. Now, I'm going to draw this a little too casually because I think I'm going to use Desmos to give me the perfect graph in a second. But it's going to go through the same key points. And I can name them really quick, like instead of 1 and 1, it's going to be 3 and 4. If I plug in 3, I get 1 over 1 plus 3, which is 4. And then I get this mirror image point on the other side of that center. Notice when I plug in 0, I get 1 over minus 2 plus 3. That's 3 minus a half. That's 2.5, or a half below that green axis. So I get these same key points. They've just been moved. And now I draw the same reciprocal shape. But I want to show you another formula for this shape and confirm it on Desmos. Because I could have done what? I could have said, here are 2 things to be added. Why don't we add these 2 fractions? You say, the second one's not a fraction. How can I add them if it's not a fraction? I say, okay, make it a fraction. Let's grab some common denominator. Common denominator would be x minus 2. And that's fine, as long as I adjust the numerator also. So So I have 1 over x minus 2 plus 3x minus 6 something kind of smells fishy to me here, but we're just going to have to go with it and see what happens. Over x minus 2. That would be creating common denominator. After I create common denominator, I have to add the two numerators. 3x minus 6 plus 1 is 3x minus 5. Now I got some legitimate questions. Are these really the same graph? I could take that to Desmos and find out. What about this 3x minus 5? Like, I believed a second ago, I saw the 2 in the graph because that's the place where I cannot go. I believe a second ago, I saw the 3 in the graph because that's the place where I leveled off. But now, what's this 3x minus 5 in the numerator? What does that represent? First, let's make sure these are the same. Let's graph them on top of each other in Desmos. Okay, so I'll go back to Desmos. Fun and games with rabbit is over. Of course, rabbits are absolutely the best pet for a math teacher. And you've probably already worked that out. Okay, this is over 2 and up 3. And why is that? Because rabbits are very good at multiplying. Let's type in 3x minus 5 divided by, whoops, got my parentheses out of place. I really screwed that up. 3x minus 5 divided by x minus 2. Now, since they're both black, they're kind of hard to see. So let me make this 1 over x minus 2 plus 3. Now the red and black thing are on top of each other, so they're hard to see. If you want to fix that, why don't I make the red thing dotted? Okay, that's a little bit easier to see that they're literally on top of each other. The red dotted curve and the black solid curve are literally on top of each other. Maybe a different color choice would make that even better. I don't know. Blue and red doesn't seem to help much. Orange and red? Orange and
So
black?
are we going to have to be able to pick out the graph transformations in the final form, like the 3x minus 5 over x plus 2?
Yes, but there's a silly, simple shortcut for doing that. But that is very good that you asked that question because I'll show you the problems in the book. Now, he's going to ask you lots of different problems, but that's exactly, where are we? Type of question that he has here in 6.8. Let me show you that. What am I talking about? Not 6.8, 6.7. He's got questions that look very much like that. And let me stop sharing, go to the next screen, where you have just simple fractions made out of simple polynomials. And here's some more complicated ones. But what you want to do, this is a fancy word, domain, what value are you not allowed to use? I'm not allowed to use 1, I'm not allowed to use 2, not allowed to use 2, not allowed to use 3. Oh, what happens if I factor the bottom? T minus 4t plus 4. I'm not allowed to use 4 minus 4. So I'm going to interpret your question like this. You're going to have to be able to read these functions. You want to be able to look at these functions and instantly say what's off limits. 5 and minus 5 in problem number 10 are forbidden. You cannot graph them. In fact, maybe I'll try to graph that in a second. But I also want you to see what to do with this 3x minus 5. Remember a second ago, I said to you, a fraction is 0 only if the numerator is 0. So when is 3x minus 5 equal to 0? Well, that happens. Add 5, divide by 3 at x equals 5/3. Where is 5/3? It's right there. 5/3 is what we call the x-intercept. It's where the graph strikes the x-axis. Where does the graph strike the y-axis? We calculated when x equals 0, that happened at y equals 5/2, 2.5. That's called the y-intercept. So here is how I interpreted your question. And it's the right question. I just want to change the words slightly. If I hand you one of these functions, the questions they're going to ask you, what's the domain? What numbers can I not use? What's the range? What numbers does it spit out? What is the x or y intercept? And those things you have to be able to find instantly. I mean, not like you just stare at it and name it. No, but you have to understand how to take this fraction and find that 5/3. Set the top equal to 0. You have to understand how to take this fraction and find the domain. Set the bottom equal to 0. You can't use 2. In this case, you have to understand, in a sense, how to find out where this thing levels off. When I write the function like this, you see that it levels off immediately at 3. When I write the function like this, it's not so obvious that it levels off at 3. Well, do you know what you could do? Oh my gosh, I'll use long division. There's a reason why we did long division. Let's take 3x minus 5 divided by x minus 2, literally. Polynomial long division, synthetic division if you want, but let's just do long division. How many times does x minus 2 go into 3x minus 5? First of all, it goes in 3 times. 3 times x minus 2 is 3x minus 6. And now you subtract. 3x minus 3x is no x's. Negative 5, subtract negative 6, be really careful, is 1, positive 1. So what is 3x minus 5 over x minus 2? You just demonstrated that it's 3 with a remainder of 1 upon division by x minus 2. You just showed me, I just showed you, either way, that these are exactly the same. So I just want to expand your question a little bit. What you want to do is anytime you look at somebody like this, you want to immediately say, what's the domain? What numbers can I use? Here's another fancy word. What's the range? That means, what numbers do I get out? You also want to say, is there an x-intercept or intercepts? There could be more than one. Are there any y-intercept or intercepts? There could be more than one. Well, no, I got to be careful. Y-intercepts, there can only be one. You find the x-intercepts by setting y equal to 0. Set this fraction equal to 0. Set this expression equal to 0. You find the y-intercepts by setting x equal to 0. Much easier to find the y-intercept. If you set x equal to 0, you get 2.5. If you set x equals 0 here, you get 3 minus half, 2.5. So this is what I want you to see. That whenever someone gives you a picture like this, you want to know these 4 things. Okay, good. I'm kind of curious now, that problem in the book. Like t minus 4 over t squared minus 16, or even t minus 2. What happens if I got some squares in there? Well, that just means there are 2 things I can't use. Let's try one out. So now this sheet is getting kind of busy and littered. I understand that. Let's say x minus 2. Desmos kind of likes things to be written in terms of x and y. And let's say divided by x squared minus 16. Well, there's a beautiful graph. And your first reaction is, whoa, that's crazy. Where'd that come from? But now you understand a little bit about where it came from. Do you see that the 2 accidents are at 4 and minus 4? The 2 places I cannot go when x squared minus 16 is equal to 0 are 4 and minus 4. Do you see this? Let me make that line solid red. Where's the y-intercept? The y-intercept is when x is 0. Put x equals 0 into the numerator and denominator. That's kind of as easy as covering up the x's with your thumb. If you said x was equal to 0, what do you get for y? 2 over 16, positive 2 over 16, because the 2 negatives cancel out. What's positive 2 over 16? It's 1/8. Do you see that point right there? 0 and 1/8. You say, is 0.125 1/8? I say, surely it is. But if you want to see it, we can type it. There's the point, 0 and 1/8. I say, does it cross the x-axis? Well, you say, let's set this equal to 0. But in some sense, that's a gift, because a fraction can only be 0 if the numerator is 0. When is the numerator 0? Only if x is 2. So I think this crosses the x-axis at 2. I come over here and look. Oh yeah, it crosses the x-axis at 2. I'll add that to the picture. Now I've got the x-intercept, the y-intercept. I know the domain. Range is a fancier word. He doesn't use that word much in this book yet. Maybe we'll use it later. It's important though. Range is exactly as I said it. What numbers do I get out for y? And you see in this picture that I can get every number down to the bottom and every number up to the top. I can find any y value I want. I can make any number I please. So the range here is all real numbers, or the whole real line. I could decorate this a little more if I added these dotted walls that I can't touch. Let me try and do that. At 4, let's make a dotted red wall that I'm not going to touch. And how about it? X equals -4. Let's make a dotted red wall that I'm not going to touch. Well, some people like dashes better. Okay, there we go. Now, I could zoom in, you know, what's the best picture here? I don't know, zooming in, zooming out. I mean, I can get lots of different details by looking at this, right? But there's probably more I could learn about this picture too. But at least I have a starting point, a basic understanding. Now let's go back. I'm going to dump all this, but let's go back to the bus driver problem. And you say, what does this have to do with the graph? Let me just get rid of all this. And you can do your own experiment in Desmos, right? What was the bus driver problem? Back to my paper for a second. I was doing 270 over x equals 270 over x plus 6 plus 1/2. But now I got a new idea. These are two graphs. If these are two graphs, then where they're equal is where they cross. Maybe I could solve the problem by typing the two graphs and see where they cross. Let's type them in. Here's 270 divided by x. Now you say, where is it? And that's probably that 270 is so big. I mean, if 1 over x we drew and 2 over x was twice as tall as 1 over x, then what about 270 over x? It must be 270 times as tall. So I think I got to do a super out zoom before I would even see it. But that's funny, look at that. I did a super zoom out, but it still has the same shape as 1 over x in a way. Now let's draw the other one. 270 divided by x plus 6. Now 6 is such a small number compared to 270, but do you see that I just took the purple thing and moved it 6 units to the right? In a way, I just moved it 6 units to the right, but that's not what I want. I want that plus 1/2.
Professor, I can't see what you're doing.
Good deal. Yes, I forgot to, at least I thought I shared screen. Okay, my fault. From the top, 270 divided by x. And notice in the ordinary window, I don't see it because 270 is so big, I have to zoom out. Okay, better. But it has the same 1 over x shape. Now let's go for 270 over x plus 6. Thank you for correcting me. And that is just 6 units to the right. I just took that red curve. Do you see 0 and 45 is the name of that point? I bet the name of this point right here is 6 and 45. It is 6 and 45. That point right there is exactly 6 units over. The blue curve is 6 units to the left of the red curve. But I don't want 270 over x plus 6. I want 270 over x plus 6 plus 1/2. Now let's look at this picture. The blue curve and the red curve are so similar. But is it possible that they cross each other? That's what I'm really interested in, is when they cross each other. Do you see Desmos is already ahead of me? Notice that it crosses at 54 and 5. It crosses when x is 54. Do you remember that was the answer to our problem? Desmos even gives me this other point over here, which I had to throw away. You know, the minus 60 miles per hour, that didn't work. Now you might say, but that looks like 4.5. No, let's not even go there. We're throwing that out because I can't drive the bus minus 60 miles an hour. Even if you drive in reverse, your speedometer doesn't say minus 60. And your odometer does not go down. Now that's interesting. I had to do a little bit of work to solve this, right? On the graph, I have the answer instantly. Well, it probably take me a little bit of work to draw this graph, sure. But you know what I could do is I could confirm my answer with a graph. X equals 54. Y equals 5. In this case, that was normally 5 hours from Sacramento to Las Vegas. Let's try the other problem. It was x plus 2 over x. Now, first of all, you say, whoa, that's crazy. Well, part of the reason why it's crazy is because now I'm at a smaller scale. That 270 was what I needed to do. I needed to zoom out really big for that 270. Let's zoom back in. This graph is a graph of x plus 2 over x. It's literally adding this line to 2 over x. Pretend you took the purple thing and you added it to the green thing. What you would get is the red thing. Think about that. As you go on and on, the purple thing is nearly 0. So you don't add much to the green thing. But as you go close to x equals 0, the purple thing shoots through the roof, and so does the red thing. So in a funny way, the red thing is exactly the purple thing plus the green thing. Okay, how does that help us solve our problem? Well, what was I trying to find? I was trying to find the moment, and I wrote it on the board, so I have to look up at my board, when x plus 2 over x was equal to 27 over 5. Let's add a line at 27 over 5, right there. And so I ask myself, are they ever equal? And I can see visually they are equal twice. Where are they equal? One of them is when x is 5. And when that happens, I get 5/4. That's 27 over 5. 27 over 5 is 5/4. And what happens at this other dot? That's 0.4. That's 4 over 10, which is 2 over 5. And what were our two answers to that problem? 5 and 2 over 5. Now, this is not the only way you could ever do that problem, right? I mean, we did the problem just strictly by flipping symbols around, strictly with algebra. But I want to plant this in your mind. Graphing may be another way to solve something. You have possibly done that before. I got to acknowledge that. But I just want to make sure everybody's on the same page. When you graph something, it'd be an easy way to check your answer in many cases. So don't overlook the graphing. Now we're still at 6-7. I wanted to do a little bit more today, and we're not moving that fast. But we're talking about graphing some basic rational functions. So with what we've said today, you could do all the problems in 6-7. And he asks you some other problems too. Let me give you one more example from 6-7. Because it's an important example, but it doesn't immediately seem connected. Let's say I write this function in a fancy functional notation. I'm looking at the problems from 13 to 22. And there's more problems on the next page like it. So if you look in that section, we got a big batch of problems that look like this. Let's go back to my paper. So let's say I give you a funny function like, I don't know, 21. This is in section 6-7. F of x equals x squared minus 3x plus 4. And you may not have done something like this before, but he says, tell me what happens if you do f of x minus f of a divided by x minus a. Then he says, tell me what happens if you do f of x plus h minus f of x over h. Now they look a little bit similar, not exactly the same, but the strange thing is in both cases, kind of the same thing happens. Let's take the easier one first. F of x is right there. F of x is x squared minus 3x plus 4. F of a doesn't take much more imagination. You just put in a for every x. What happens when you subtract them? X squared minus 3x plus 4. Subtract a squared minus 3a plus 4. And not only subtract them, but after you do that, divide by x minus a. Let's work out what this is. Say, in the top, you don't got anything that combines except 4 minus 4. So you have x squared minus a squared minus 3x minus negative 3a means plus 3a, and then x minus a. Excuse me. Now it's got some similarities going on here, so you might be saying, oh, maybe I can factor. Well, how about grouping? First two, last two. The first two factor into x minus a, x plus a. That's the difference of two squares. The second two people both have a negative 3. And if I remove a negative 3, I'm also left with x minus a. I consider that excellent because that means in the top, I have two pieces that both have an x minus a. I can factor again. This is factoring by grouping. So if I factor out that x minus a in the top, what am I left with? X plus a and minus 3. What do I have on the bottom? An x minus a sitting there like it was waiting for me. And it was. Now I get to cancel these two x minus a's. So the answer is, they said, what happens when you do this? The answer is, this is what happens when you do this. I get f of x minus f of a over x minus a turns out to be x plus a minus 3. Over here, it takes a little more work, and I think I can squeeze it in 2 minutes. So just be patient with me. I'm going to do the same thing. I know what f of x is already. What's f of x plus h? That means stick an x plus h in for every x. But that requires me to FOIL this out. X squared plus 2xh plus h squared minus 3x minus 3h plus 4. So that looks like a long string of stuff. So what happens if I take that long string of stuff and I subtract the original stuff? Let's write it out. X squared plus 2xh plus h squared minus 3x minus 3h plus 4. That's just the f of x plus h. Now let's subtract f of x. Subtract x squared, subtract x squared minus 3x plus 4. What do I get? X squared minus x squared going to be canceled out. Subtract 3x. Here's a negative 3x, and here's a subtract negative 3x. Negative 3x plus 3x cancels out. I'll double cross them. What about 4 minus 4? Cancels out. Cross the other way. I used up all these people over here. What's left? All that's left is 2xh plus h squared minus 3h. Something doesn't feel good. What doesn't feel good? I can't worry about it right now. Let's go forward and see what happens. Now they wanted me to not just do all that, but after I got done doing that, divide by h. So let's try it out. 2xh plus h squared minus 3h. But let's divide by h. Now everybody up top got an h, so I can factor that out. 2x plus h minus 3. And there's that h in the bottom. This much is like the last problem. It's just sitting there waiting for me to cancel. So f of x plus h minus f of x divided by h. This is some kind of game, some kind of puzzle we were solving. Turns out to be 2x plus h minus 3. Now, actually, we did this correct. This is good. They were supposed to be similar, but not the same. Now, you could be saying, they don't look similar at all to me. Well, some of it you do have to acknowledge. Minus 3 to minus 3. But it might be for another math class for me to tell you why these are very much representing the same thing. I'm just going to let that be right now because we're at the limit of our time. Okay. Why is this in this section? Because it's a rational function. It's a fraction made out of polynomials. And when you learn how to simplify rational functions, that means you learn how to simplify new things. This is a fraction made out of polynomials. So he thought this was a good time to show you this problem. The fancy word for this animal, either on the left or on the right, is called a difference quotient. Okay, so you'll see him referring to the difference quotient in the homework problems. That's what a difference quotient is. Either one. Okay, I'm gonna have to let that be for right now because that's the limit of our time. Now, I picked up a cold over the weekend. Hopefully you didn't, but it is promised to be a little bit of warm this week. So make sure you get outside because, we're heading for more cold than warm. So just enjoy last week of warm if this is the last week of warm. It may be. You guys have a good day. I'll get this all posted and then you can go on with your work. Talk to you later. Bye.